September 1941. Muroc Dry Lake, California. The desert air shimmers at 38 degrees Celsius. A prototype aircraft sits on the cracked earth. Its fuselage, unlike anything that has ever flown. No propeller at the nose, no piston engine humming behind the cowling. Instead, two tubular housings extend beneath the wings, and inside them, air is being compressed, mixed with fuel, and ignited in a continuous cycle that engineers are still arguing about in theoretical journals. The aircraft is the Bell XP-59A. The engine is a copy of a British Whittle W2B turbojet smuggled across the Atlantic in a wooden crate labeled Freight. The American pilot, climbing into the cockpit, has never flown a jet aircraft. Neither has anyone else in the United States. In 36 months, America will have 12 operational jet squadrons. This is not a story about borrowing British technology. It is a story about what happens when an industrial civilization, confronted with a gap of a decade in aerospace physics, decides that closing it is a matter of national survival and gives the problem to engineers who have never heard the word impossible used as a reason to stop working. The gap nobody wanted to admit. In 1939, Frank Whittle had already been working on jet propulsion for 11 years. A Royal Air Force officer who had proposed the concept in his Cambridge thesis in 1928, Whittle filed his first patent for a turbojet engine in January 1930, the same year the American aircraft industry was still debating whether to switch from fabric-covered biplanes to all-metal monoplane construction. The gap was not merely technological. It was conceptual. American aviation in 1939 was the most productive piston engine aviation industry in the world. Curtiss, Pratt & Whitney, Wright Aeronautical, these were companies of extraordinary competence in a technology that had reached its limits. A Pratt & Whitney R2800 double wasp radial engine, the finest piston aircraft engine built during the war, produced 2,000 horsepower from 18 cylinders, displacing 45.9 liters of combustion space. It was an engineering masterpiece. It was also the end of a road. At speeds above 500 miles per hour, propeller blades began compressing the air in front of them, creating shock waves that destroyed efficiency. Physics had drawn a line. Piston engines could not cross it. What Whittle understood, and what American engineers were slower to grasp, was that the turbojet engine is fundamentally different in its operation principle. A piston engine converts chemical energy into reciprocating mechanical motion, then uses that motion to turn a propeller. Every conversion involves losses. A turbojet converts chemical energy directly into thrust by expelling hot, high-velocity gas. The thermodynamic cycle, the Brayton cycle, is continuous rather than intermittent. There are no pistons, no crankshafts, no valve timing, no cooling fins. Just compression, combustion, and expansion in a single uninterrupted stream. The United States Army Air Forces understood by mid-1941 that Germany had operational jet aircraft in development. The Heinkel HE-178 had flown in August 1939. The Messerschmitt ME-262 was under development and would enter service by 1944. American military planners ran the strategic mathematics and arrived at an uncomfortable conclusion. If jet-powered German fighters entered the war in significant numbers before the United States had an operational jet program, Allied air superiority, the foundation upon which every offensive plan rested, would collapse. ¿Cómo jet planes funcionaban? The Crate from England. In September 1941, General Henry Hap Arnold flew to Britain and saw the Gloucester E-28/39, the first British jet aircraft, fly. He returned to Washington with a decision already made. Within days, he had authorized a top-secret program and contacted Bell Aircraft Corporation in Buffalo, New York. Bell was chosen not because it had jet experience, nobody in America did, but because it was small, aggressive, and not already drowning in production contracts for conventional aircraft. Dentro de días, autorizó un programa secreto y contactó a Bell Aircraft Corporation in Buffalo, New York. General Electric was assigned the engine. This choice was deliberate and counterintuitive. GE had no aircraft engine division. Its aircraft work had been in superchargers, devices that compressed intake air for high-altitude piston engines. But supercharger engineering is compressor engineering. A turbojet is, at its core, a compressor attached to a turbine. GE's engineers understood axial flow compression in ways that Pratt & Whitney and Wright Aeronautical, whose cultures were built around reciprocating engines, did not. The British engine arrived in October 1941, a Whittle W2B, 1,600 pounds of thrust from a centrifugal flow compressor spinning at 16,500 RPM. GE's engineers at Lynn, Massachusetts, disassembled it component by component. They measured every dimension. They analyzed every alloy. They tested every tolerance. Then they built an American version, the GEIA, that produced the same thrust from components they could manufacture in the United States from materials available through American supply chains. What they discovered inside that British engine taught them more thermodynamics in 6 months than a decade of academic research had produced. The combustion chamber temperatures exceeded 800 degrees Celsius. The turbine blades, spinning at velocities that created centrifugal forces equivalent to 30,000 times their own weight, were operating in a thermal environment that no metallurgy of the time was designed to withstand. British engineers had solved this problem empirically through trial and catastrophic failure over 11 years. GE's engineers had to understand it analytically from first principles in months. The metallurgy problem at the edge of known science. The turbine blade is the most stressed engineering component in a jet engine. It must simultaneously withstand temperatures that approach the melting point of the alloys from which it is made, centrifugal stresses that would rip apart most structural metals at room temperature, and thermal cycling that expands and contracts the metal thousands of times per flight hour. In 1941, no alloy had been designed specifically for this combination of demands. The solution came from an unexpected direction. Haynes International, a specialty metals company in Kokomo, Indiana, had been developing nickel-chromium alloys for chemical processing equipment, industrial reactors that needed to resist both high heat and corrosive attack. Their alloy S816, a cobalt-based superalloy, had properties that nobody had anticipated would apply to aerospace. Cobalt provided high temperature strength. Chromium provided oxidation resistance. Tungsten and molybdenum provided creep resistance, the property that prevents metal from slowly deforming under sustained stress at high temperatures. The engineering collaboration that followed was unprecedented. GE's turbine designers worked directly with Haynes metallurgists to understand how alloy composition affected both manufacturing properties, could it be cast into the precise airfoil shapes required, and operational properties, would it maintain those shapes at operating temperature and stress? The answer required simultaneous advancement in three fields: alloy chemistry, precision investment casting, and high-temperature fatigue testing. None of these fields, in their existing state, was adequate. All three were advanced in parallel, under time pressure, by teams that had never worked together before. The combustion chamber presented a different problem. Jet fuel, kerosene-based, heavier than aviation gasoline, had to be atomized into droplets fine enough to achieve complete combustion within a chamber small enough to fit inside an aircraft nacelle. Incomplete combustion meant lost thrust and carbon deposits that could block fuel injectors. Complete combustion in an insufficiently cooled chamber meant temperatures that destroyed the chamber walls within minutes. The engineering solution, a double-walled combustion liner with precisely calculated cooling air gaps, required airflow analysis that barely existed as a discipline in 1941. Bell aircraft and the airframe that didn't exist yet. Larry Bell, founder of Bell Aircraft, received his project authorization in late September 1941. His engineering team had exactly 13 months to design, build, and fly a jet aircraft from a blank sheet of paper. The only reference material was a collection of British reports on the Gloucester E-28/39, itself a technology demonstrator, not a combat aircraft, and a set of preliminary performance estimates for the GE-IA engine that GE's engineers were still revising as they learned more about how the engine actually behaved. The challenge was not merely mechanical, it was conceptual. A jet-powered aircraft behaves differently from a propeller-driven aircraft in ways that were not fully understood in 1941 because no American engineer had ever flown one. A propeller creates a slipstream that flows over the fuselage and wings, contributing to lift and control. Remove the propeller, and the aerodynamics change fundamentally. The center of thrust shifts rearward, control surface effectiveness at low speeds decreases. The aircraft's behavior during engine failure becomes entirely different. Robert Woods, Bell's chief designer, made several decisions that would prove prescient. He placed the two engine nacelles under the wings rather than burying the engines in the fuselage, a configuration that made engine access and replacement easier, reduced fire risk to the airframe in case of combustion problems, and simplified the inlet ducting that was proving to be one of the most aerodynamically complex aspects of jet engine integration. He used a tricycle landing gear, then considered unconventional, because jet aircraft takeoff and landing characteristics were unknown, and a nose wheel configuration provided more stable ground handling in the event of the unexpected. The XP-59A first flew on October 1, 1942, 13 months after project authorization. It was not a successful combat aircraft. Its top speed of 413 miles per hour was actually inferior to the latest piston fighters because the GE-IA engine produced less thrust than British or German jet engines then in development. But that result, disappointing as it appeared, was beside the point. America had built a jet aircraft. Its engineers now understood, viscerally and quantitatively, what jet propulsion required. The gap between theoretical knowledge and embodied engineering competence had been crossed. The acceleration from prototype to industrial scale. What followed the XP-59A program was less a single development effort than an industrial explosion. GE, having learned the fundamental engineering of the centrifugal flow turbojet from the British Whittle design, simultaneously began development of an axial flow engine, the I-40, which would become the J-33, that promised significantly higher thrust and better high-altitude performance. Lockheed Aircraft, assigned to design a combat-capable jet fighter around the city, gave the project to a team led by Clarence Kelly Johnson, who set up what would become famous as the Skunk Works, a small, isolated engineering group operating with minimal bureaucracy and maximum urgency. Johnson's team designed the Lockheed P-80 shooting star in 143 days. The first prototype flew in January 1944. With a thrust of 3,850 pounds from the GE I-40 engine, the P-80 achieved a top speed of 558 miles per hour, faster than any piston fighter then in service and competitive with the Messerschmitt Me 262. The engineering progression from the XP-59A to the P-80 in 15 months represented an acceleration of technical competence without precedent in aerospace history. In those 15 months, American engineers had not merely improved a design, they had developed an entirely new engineering culture. The production engineering presented a different set of problems. Jet engines required tolerances, the permissible dimensional variation in manufactured parts, tighter than anything American industry had previously attempted at scale. A turbine blade that was 0.003 inches too long would contact the casing at operating temperature when thermal expansion brought the blade tip to within thousandths of an inch of the housing wall. A compressor blade with incorrect airfoil curvature would generate shock waves that reduced efficiency and could cause compressor stall, a violent disruption of airflow that could destroy the engine. Manufacturing methods adequate for propeller-driven aircraft were inadequate for jet aircraft by an order of magnitude. The solution was the systematic application of what would later be called statistical process control, the monitoring and analysis of manufacturing variation to identify and eliminate sources of dimensional error before defective parts were produced. This approach had been developed theoretically by Walter Schuhart at Bell Telephone Laboratories in the 1920s and championed by W. Edwards Deming, but it had seen limited industrial application in the United States before the jet engine program created an absolute requirement for precision that conventional quality inspection, measuring parts after manufacture and discarding those outside tolerance, could not economically satisfy. The psychology of forced innovation. What drove engineers to achieve in 18 months what peacetime research programs had failed to accomplish in a decade? The answer lies in a well-documented psychological phenomenon, the elimination of optionality. In peacetime, an engineer who encounters an apparently insoluble problem has options. He can redirect resources to a more tractable problem. He can await theoretical advances that might simplify the practical challenge. He can write papers suggesting that the problem is harder than previously understood and that more research is needed. Under the conditions of 1941 to 1944, none of these options existed. The problem had to be solved. The timeline was fixed by external strategic reality, not internal engineering preference. This constraint forced a cognitive shift that psychologists who study problem solving would recognize immediately. When retreat is impossible, the human mind commits to advance with a focus and creativity that optional problems never produce. The engineers working on the XP-59A and the P-80 were not smarter than their peacetime counterparts. They were operating in a psychological environment that made certain cognitive shortcuts unavailable. There is also the question of what sociologists call collective intelligence amplification, the phenomenon by which groups of people working in close proximity on shared problems develop problem-solving capabilities that exceed the sum of individual contributions. Kelly Johnson's Skunk Works model Small teams, minimal hierarchy, direct communication between all contributors regardless of institutional rank was an accidental application of principles that would not be formally theorized until decades later. When a manufacturing engineer could walk directly to a designer's desk and say, "This feature cannot be manufactured to the required tolerance with available tooling," and receive an immediate design modification rather than a memo that would take 3 weeks to traverse an organizational chart, the feedback loops that drive innovation compressed from months to days. What history records and what it omits. The standard historical narrative of American jet development in World War II emphasizes the XP-59A's disappointing performance and the fact that the P-80 arrived too late to see combat. Both statements are accurate, and both miss the essential point. The XP-59A's purpose was not to shoot down German fighters. Its purpose was to create, in the minds and hands of American engineers, the embodied knowledge of jet propulsion that could not be acquired by reading British reports. In that purpose, it succeeded completely. The P-80's failure to enter combat before Germany's surrender in May 1945 is presented in some accounts as a near miss of strategic significance. This framing contains an implicit counterfactual worth examining. What if Germany had been able to deploy the Me-262 in larger numbers earlier? The Me-262 entered operational service in July 1944, with approximately 300 aircraft eventually completing production by war's end. Allied air forces countered it primarily by attacking airfields where the aircraft were taking off and landing. Jet aircraft of the period were most vulnerable during their slow acceleration phase before reaching operational speed. The P-80 would not have changed this tactical calculus significantly. What it would have changed was the long-term strategic balance had the war continued into 1946. More significant than the P-80 itself was the industrial and engineering infrastructure that producing it created. By 1945, the United States had jet engine manufacturing capability distributed across GE, Westinghouse, and Allison, 3 independent industrial centers with complementary technological approaches. It had aeronautical testing facilities capable of evaluating transonic flight characteristics. It had a pool of engineers with first-hand experience of jet propulsion problems and solutions. This infrastructure was the real strategic achievement of the 18-month program. When the Cold War began in 1947, it was the foundation on which American air power was reconstructed. The lessons that outlasted the war. The American jet engine program of 1941 to 1945 demonstrated several principles that have been repeatedly validated in subsequent technological history. First, that the gap between understanding a technology theoretically and possessing it practically is larger, more qualitative, and more difficult to bridge than any written description of that technology suggests. GE's engineers had access to Whittle's patents. They had the physical engine to measure and analyze. They still required years of operating experience before they understood the failure modes, manufacturing requirements, and operational characteristics of the technology at the level required to advance it independently. Second, that industrial infrastructure and engineering culture are strategic assets of a different order than weapon systems or production capacity. The United States could have purchased additional P-40 Warhawks or P-47 Thunderbolts with the resources invested in jet development. Those aircraft would have contributed to winning the current war. The jet program contributed to determining the technological character of all subsequent conflicts. The distinction between resources that win the current competition and resources that determine the terms of future competition is one that strategic planners have rarely made with sufficient clarity. Third, That the organizational innovations that emerged from the wartime jet program, small teams, compressed hierarchies, direct communication between specialties, tolerance for failure as a learning mechanism, proved more durable and more broadly applicable than the technological innovations themselves. Kelly Johnson's Skunk Works model has been replicated, with varying fidelity and varying success, in defense and commercial aerospace, in Silicon Valley, in pharmaceutical development, and in dozens of other fields where rapid innovation under constraint is required. The P-80 was superseded within a decade by faster, more capable aircraft. The organizational principles that produced it remain influential 8 decades later. Fourth, and most troubling for those who draw simple lessons from technological history, the 18-month compression of the jet program required conditions that cannot be deliberately engineered in peacetime. Genuine existential urgency, complete organizational commitment, and the psychological effect of removed optionality on individual engineers and managers. Attempts to replicate the results of wartime innovation programs in peacetime commercial contexts have consistently underperformed expectations, not because the people involved were less capable, but because the organizational and psychological conditions were fundamentally different. The thermometer on the tarmac at Muroc. On October 1, 1942, when Bell test pilot Robert Stanley lifted the XP-59A from the salt flats at Muroc, an event so secret that a dummy propeller had been bolted to the nose to confuse any casual observers, the aircraft climbed to 10,000 feet and flew for about 30 minutes before landing. The engine performed without incident. The airframe responded to control inputs as designed. There was nothing spectacular about the flight. It was, by any objective aeronautical standard, unremarkable. What was remarkable was invisible to anyone watching from the ground. It resided in the minds of the engineers who had spent 13 months acquiring, through necessity rather than preference, a depth of practical knowledge about jet propulsion that could not have been purchased, borrowed, or theorized into existence. That knowledge, distributed across hundreds of engineers at Bell, GE, Lockheed, and a dozen supporting contractors, was the real payload of October 1st, 1942. Frank Whittle, who received a knighthood in 1948 and eventually moved to the United States as a research professor, spent his later years expressing frustration that Britain had failed to capitalize commercially on the technology he had invented. American companies, GE, Pratt & Whitney, came to dominate the global jet engine industry, not because they had invented the technology, but because they had built the industrial and engineering infrastructure to advance it. The lesson Whittle drew from his own story was that invention and exploitation are different activities requiring different organizational conditions, and that a nation that excels at the first does not automatically excel at the second. From October 1942 to August 1945, the United States went from one barely flying jet prototype to an operational jet fighter force. The technology had been borrowed. The engineering competence was built. The industrial capacity was created from nothing. The organizational innovations were discovered accidentally and applied instinctively. None of it was planned with the clarity that retrospective accounts suggest. Most of it was improvised under pressure by engineers who were making decisions whose consequences they could not fully anticipate, in a domain where the existing body of knowledge was insufficient to answer the most important questions. That is what compressed innovation actually looks like. Not a plan executed with precision, but a constraint applied with sufficient force that the usual barriers to progress, risk aversion, organizational inertia, the comfort of existing competence, become less costly to overcome than to maintain. The jet program did not solve physics. It solved the political economy of risk-taking by making the alternative to risk-taking catastrophic. America entered 1941 without a jet engine. It entered 1944 with an industry. The 18 months in between were not a story of American ingenuity. They were a story of American necessity, and of what necessity, properly structured and sufficiently urgent, can compel ordinary engineering organizations to become.